Hello, everyone. Well, thank you very much for choosing this as your final talk of the day. I wonder how many people are here just to make sure they get a seat for the movie, because you could just stay here. Yeah? Maybe. I would have probably done that. So this talk is going to be from practical experience I had building a large system over the course of 18 months to 2 years. By the title of the talk, you can probably realize that we did go down a microservice route. This was a few years ago, so we weren't really calling it that. We were just calling it multiple medium-ish services that interact with each other over a network. I normally title this slightly more negatively, though. The dangers of microservices. So don't worry, there's no microservice going to hurt you or anything, but they could keep you up at night. Because probably the most apt title I think I can come up with is this one. Because this is pretty much what happened to us. Lots of different things happen when you decide to spread your logic over many, many servers. I spent a long time working on services spread across many servers, as well as working with distributed databases. So yeah, stuff does happen. A little bit about me. I'm a freelance developer / consultant. The system I'm talking about was built at a large-scale internet television provider over in the UK. I then spent time working for the company behind Apache Cassandra DataStax, and now I'm back freelancing mainly at the same company I was at before. I do lots of work with building out platform for them with Docker, Kubernetes, and large amounts of Cassandra and large amounts of JVM services running inside Docker containers. I spend a lot of time working with Cassandra, but also use lots of other databases. I also work for a little company called The Last Pickle. These are the best Cassandra consultants in the world, so if you actually want some help with this stuff, then go and speak to them. If you happen to be from the UK and London, and you want a job, then come and work at my main client right now, because they are hiring heavily. If this stuff interests you, I'm working on a massive new greenfield project, and we need another 20, 30 people, so do come and talk to me afterward. Anyway, on to the real stuff. So, we'll define what we mean by a microservice. I've got a very good definition for that will trump all other definitions. We'll talk about what type of faults we're going to deal with, and then you're not going to get 6 principles. I apologize. The title of the talk has lied to you. We're only going to get 5, but we're going to get a live demo of 1. Because the last time I did this talk, someone came to me after and said they didn't believe me. They said, that can't happen. No. So we're going to do a live demo, which could go terribly, which I guess will be entertaining for you as are embarrassing, or it could be a good demo. We'll see. One of the emphasis of this talk, though, will be anything that can happen in production, we can reproduce locally in our, say, continuous integration environment. I don't believe that you can classify something as a network glitch and then say it only happens in production. I'm going to talk about ways in which we can build automated tests to recreate things like saturated and slow networks. So a bit of background about this system that I built. It started off with a cat, like most great stories. Tomcat in this instance. And it was some time ago now when internet television was not popular. We still had to turn up at 9 p.m. to watch our favorite program. Yet the company I was working for at the time, they thought, maybe people will want to watch Game of Thrones on an iPad on a toilet, even though iPads didn't exist probably, and neither did Game of Thrones. And it did. It got popular. So by the time I got there, it looked more like this. It was many, many Tomcats with a nice, expensive load balancer in front. However, this application had not been built with horizontal scalability in mind. So it is using lots of our friends called session state. Right? So as soon as someone was logged in and watching a program, then they had to be pinned to that node. It had sticky sessions. And what generally happened is either one of 2 things. The first thing is the database would fall over. It was a database produced by our favorite company here, Oracle, and sometimes it wouldn't keep up with the fact because we weren't necessarily scaling the database. It may have been running on a larger server, but we weren't horizontally scaling it, but we were running more and more instances of our application. If that didn't happen, then we'd normally need to take down a couple of cats. Now, these could fall over, they could just run out of memory, they could have something to do with permgen, who knows. And what would generally happen then is all of the clients that were logged onto these servers would come out, they'd be logged off, which generally means you end up with unhappy clients. But more importantly, they come back to the load balancer, it can't be a sticky session now because that server doesn't exist anymore, and then this happens. It takes down everything because we have all of those users coming back and hitting all of the rest of them. So what are we going to do about that? Well, what do you think? The main thing that caused this to happen, though, two big reasons. And we'll forget about technology for a moment, and we'll talk about the true problems to see whether we could solve those. If we could just get rid of Game of Thrones, because every time there's a new episode of Game of Thrones, this would happen, because it's ridiculously popular, and a silly football team called Manchester United, because everyone in the UK wants to watch them. And actually one of the biggest events in terms of concurrent users on this system was when Manchester United used to get to the knockout stages of the Champions League, and they happened to play Real Madrid. But hey, what are we going to do about it? So we decided to work out which parts of that application were actually causing it to fall over. There was a particular area which hit the database extremely hard. It was keeping track of every single event that happened, whether someone logged on, logged off, watched Batman, turned off after Real Madrid scored, who knows. And that they all need to be persistent, and that would also be used for billing. So that needed to be properly persisted, and it was putting too much load on the database. The other was a service which was what we needed to do for every device that was watching television. It would need to keep a session open with it, and it need to heartbeat. We stopped people from watching, using their account on multiple services, and you need to keep this going. So we wanted to separate these into small components, maybe microservices, and have them running separately and scale them separately. We didn't do this right away, so we did the classic pattern of pulling small sections out, the bits that were actually causing it to fall over, to buy us time to eventually, replace the entire system. And one of the other architectural principles we followed was that each application then got its own database. So never did two services share a database. We happened to use Apache Cassandra for everything, but they were separate clusters. They were separate database instances. And then eventually, what does it actually look like now in production? It's lots of services, all with their own database cluster, and everyone lived happily ever after. So we're going to go through all of the 5 principles now. You don't get the 6th. That essentially had to change my mindset to still be successful building software this way. And I pulled out a little example, which of course is on GitHub, like the rest of the world. And we're going to do some demos. We're going to have a look at some code, etc. The technology involved, we're going to use Drop Wizard. So no Spring, no JEE, sorry. We're going to inject faults into our system using a really cool thing called Wiremock. If you haven't heard of Wiremock, you will leave this wanting to use Wiremock lots, because I love it. We won't talk much about Hystrix, but I'll just tell you it's there. And we're going to use a really cool tool called Saboteur. What Saboteur is a wrapper around a few Linux commands which enable us to, say, slow down packets in a network, etc. Which means that we can actually create deterministic tests of things which previously we'd just say, it's a network glitch. Anyone ever had that? No, it was GC followed by a network glitch. That's the best excuse. So, what do we mean by a microservice? Well, here's mine. You don't need a dependency injection framework. This is opinionated, don't worry about this, but yeah, we mainly use Drop Wizard just by itself. If we're going to have a small Java service, I can put things into a constructor myself, so don't worry too much about that. The other part of the thing is we're going to be creating tests. So the organizations I've worked at recently have been really quite good at having automated acceptance tests for each piece of functionality that we deliver. Right? If you don't have an automated acceptance test, I don't think it's a feature, it's more just a rumor. Might be there today, might be gone tomorrow, who knows. But what I really want to encourage is for all of the different faults that can happen in our system, we also have a test that runs, and we want it to be a quick test. I don't want to wait until I get to my, say, single component NFT, which does a soak test over, say, days and weeks. I want to find 99.99% of the problems early on. And I want, as soon as I check in my code, for some automated test to build and to find these faults. And if we miss one, which we obviously do, when we actually come to reproduce it, the first thing I want to do is create an automated test for it before I fix it, to actually prove that we fixed it. So yeah, you don't know things are fault tolerant if you don't test faults. We're going to use lots of test doubles for this. And I don't mean something like in process, so Makito, etc. Go ahead, do that. That's fine. But the type of tests we're going to talk about here are going to use something I call a protocol level test double. So this means that when our service is interacting with it, let's say we build a WAR file and deploy it to Tomcat, or we build an executable jar with an embedded Jetty. When we're testing that in isolation, then it's going to interact with test doubles, and it's not going to realize that they're not the real thing. So it's going to be real TCP. For HTTP, of course, it's going to be HTTP, and we're going to use Wiremock. I spent my evenings and weekends building the equivalent for Cassandra, so you can pretend that you've got a 30-node cluster and pretend half of them are down and see if your application actually handles it. And I started playing around with one for Kafka. And this is, a lot of the concepts for this was stolen from Release It, which is a fantastic book that predates this whole microservice thing. But it's actually talking about, problems in connection pools between two very large monolithic applications. So these are what the tests are going to look like. We're going to have a protocol level test double pretending to be our dependencies, and I'm typically going to run that on a virtual machine for reasons that we'll see soon. We're going to be deploying our service exactly like it is in production. If it's in a Docker container, that's what it will be. If it's an executable jar, that's what it will be. And it's all going to be real protocol here. As far as I'm concerned, if you bring a jar into your application that you say is yours and you test and you say it's ready for production, the jars, even the dependencies, even if they're from a different company or they're from the internet, because everything is trustworthy on the internet, then that's part then of your process that you're supporting. And I test those as much as I would test my own business logic. I do in a different way. It's not typically unit testing of logic. It's basically putting it under adverse failure scenarios, which we'll do today. So let's get on to the principles. As you'll notice, we've only got 5, but we're going to demo the first one. We're going to show that if your dependency trickles network traffic back to you, you can block forever regardless of what network level timeouts you set. So why should we time out quickly? Well, let's say we've got multiple instances of our application. We could be an individual instance which is misbehaving, etc. We want our clients to be rerouted to another one. In some of my favorite technologies like Cassandra, having a slow node in a distributed system is vastly worse than having a dead node. People wait for it, and then everyone blocks, and it cascades all the way up your dependency hierarchy. So even if your business do not give you SLAs, define them yourselves, technical SLAs, and define them, say, at the average and then a percentile level. And you want your services, you want tests to fail if for any reason you can go above this. So which timeouts are we going to set? So we're going to concentrate on when we're calling out over the network. So HTTP clients, database clients, queuing clients, all of these things that reach out over the network. Though some of this is applicable regardless of what the code's doing. And the first thing you generally look at, and hopefully you have these settings on your HTTP client, etc., are of course your socket connection timeout, the amount of time it takes to establish a TCP connection. And the default for this on most systems is something around 4 minutes. And you probably don't want your SLA to be 4 minutes, so we want to set something there. Once we've actually established the TCP connection, then we want to time out waiting for data to come back. And the default here for most systems is unlimited. So if you have a nice firewall that sits between you and your dependency and it decides to drop your connection without setting a reset either way, then things can hang forever. This happened to me in one company where everybody interacted via WebSphere The firewalls had knocked down all of the connections, and every single service was up and happy. Everything was hunky-dory. However, the whole system, from the customer's point of view, was frozen. So we had like health checks and status checks going to each individual application, but absolutely nothing worked. And if we set these 2 timeouts on all of our database drivers and HTTP clients, and we stop using the ones that don't let you set them, then everything's going to go really well, but not for long. Right? If we only rely on network level timeouts, some bad things will eventually happen. There'll definitely be a sad panda involved, and you'll eventually get shouted at. Because I work as a freelancer, I might not get paid, which is a really bad thing. So what do we do next? So we've set these 2, and we're good to go. So what else can take time? Apart from garbage collection. We won't talk about garbage collection today. Well, the next is resource acquisition. So most of these HTTP clients and database drivers that we use, they, or I hope they don't, do not make a separate connection and use a separate request every time you ask them to. Otherwise, you'll do some kind of distributed denial of service on your dependencies if you get a flood of traffic. So they normally have a very small pool of connections, maybe 5, 10, etc. Or if you're using a technology like Cassandra where you can multiplex over the same connection, it might be 2, it might be a very small number, 2 or 3. So imagine you fix this, you realize that you can set this. And when you think about it, it becomes intuitive because if you go into your piece of code, which is, say, a database driver, and before they even send your request, before we get anywhere near the network, it's waiting. It's in a queue. It's waiting for a connection to become available. You haven't gone near the network, so obviously the other timers haven't started yet, which is why it can take much longer. But if you find this, you'll become the hero. You'll set this, and your customers will be very happy until they're not. And eventually, it will hang again. And someone will blame it on the network. They'll say it's a glitch, and they're not sure what to do. And this is exactly what someone told me they didn't believe. So this is what we're going to start to do a demo. If we quickly try and analyze what's happening, though, before we demo it, I like to draw diagrams when I don't understand how something's working, and I didn't when this first happened. So we've set these 3 timeouts. We've set a resource timeout, we've set a connection timeout, we've set the socket read timeout. Surely this can't take more than 700 milliseconds plus or minus some. Maybe not. So we're gonna create an automated test for it. I will be the test executor rather than something like Cucumber or some framework. But anything I do here is very easily automatable. We're going to use Vagrant to do it, and this is so we can spin up a VM to run our dependencies in. Now, most self-respecting ops people are not going to let you to run things like IP tables and TC, etc., on all of your continuous integration machines. So that's why we're running it inside of a VM. It's also very useful that if in a repository, and it's a repository for an application which has many dependencies, that if you include a Vagrant VM, a Vagrant with it, then you can actually spin up and it can be self-contained, etc., and someone doesn't need to get dependency X, Y, and Z to get it running. One of the things we're going to run inside that VM is Wiremock. That's going to pretend to be an external HTTP service. So it's going to look a bit like this. Just like the picture at the start, except we're going to sneak Saboteur in the front, which is then going to play around with IP tables and TC, and it's going to slow down network. So during the demo, to keep you focused, these are the things you need to remember. If we're hitting this IP address, so I'm hitting an IP address, it's 192.168.2.2, I'm inside the virtual machine. It's where my dependencies are running. If I'm hitting localhost, that's going to be our application. We're just going to be running that inside IntelliJ, and we're going to be interacting with it from curl. Wiremock allows you to prime it. You can do things like, when someone calls you on /name, return Chris. 200. Or you can say 500, or you can say delay the response for a while and see what happens. So and you can prime it over a HTTP interface. So when I'm doing priming, it's going to be over this thing here. This is the Chrome Advanced REST client. So this is going to be priming Wiremock. When we actually interact with our service, when we're pretending to be our test, we're going to be doing it with curl on the command line. So that's just a thing to keep in your mind. If I'm inside Chrome Advanced REST client, we're doing a prime. If we're on the command line, then we're going to be hitting our service and seeing what happens. So let's see what happens. So I got a couple. This looks big enough. That's the advantage of being in a cinema. So on this side, on the left, we've got localhost. This is where we're going to be interacting with our service. On here, I've got a VM. So this is Linux, because we're going to be using some commands which don't exist on Mac OS X. And then this is localhost. This is the service we're going to be playing with. It's a really important one. It's called Enterprise Hello World. And what it's going to do is it's not going to say hello to the world. It's going to be more specific than that. It's going to say hello to a particular individual. This is DropWizard and it's Jersey. So all it's going to do is make a call out. This is the Apache HTTP Fluent API. It's going to execute a request. It's going to return the content as a string. And then it's going to return the response hello, followed by whatever came back from the external service. So this is microservices 101, right? We just spread it into 2 separate services. And this is going to be running on say hello. We can start this up, or maybe I've already started it. We'll start it up. I'm actually wearing a zero turnaround t-shirt and restarting my Java application. There's a certain irony there. It'll tell me off. So let's see here. The other thing I'm going to do is time everything. So I've got time, curl, which is just a command line, thing for hitting HTTP. And we're going to go to localhost 8080, say hello. And what did we get back? We got back a 200 OK, so everything's good. And it said, hello, Chris. Wiremock is default prime is to respond with Chris when you call it on /name. And this took a whopping 400 milliseconds, and that's just because it's the first time I hit this service. If I hit it again, we're down to 19 milliseconds. Can everyone see that, or should I? There we go, 19 milliseconds. What we can also do is hit our dependency directly. So here, I'm actually going to hit 192.168.2.2. So this is not going through our application under test, this is going directly to our dependency. And that just responds with Chris. So the first thing we'll show you how you can use this for happy path testing. So with Wiremock, what you can do is you can go to its admin interface, which is running on this URL. Don't worry about the syntax of Wiremocks. There are many different pieces of tech which can do this. But it's pretty intuitive. You say, when someone calls you with get on/name, return a 200, but this time we're going to change our name to Brady. So our microservice that we're calling out to is going to change its behavior. This is to prove you that it's a dynamic call out. So once we've done that prime, I can call it again, say hello, and hopefully it should say hello Brady instead of hello Chris, which it does. Fantastic. That is not very exciting though. Let's start doing something more exciting. One of the coolest features of Wiremock is to be able to delay responses but have them still be successful. So here, we're going to be at 200. It's still going to be Brady, so we haven't moved back to Chris, but we're actually going to delay the response by 20,000 milliseconds. Let's make that 10,000 milliseconds. So here we've got the fixed delay milliseconds. So I'm going to send that in. And then we'll hit our service again, and we're hanging. So now I need to entertain you for 10 seconds while this finishes, which is not a good thing. If we were monitoring these separate services, we would show the name service as being slow. And we'd maybe call the developers up and say, hey, your service is slow. But our service as well, that's also being slow. You know, we haven't narrowed down the problem. We've got a cascading failure because service X has been slow, service Y, which calls out to it, is also been slow. So this isn't very good, and we shouldn't do this. Imagine this if you've got 50 microservices and you've got one calling another. You know, you'll never finish a response. So let's change the code a bit. So this API is pretty intuitive. We can do socket timeout, and it's in milliseconds. So maybe we can set it to 500. So we're starting along the line of having the technical requirement that we want to either respond within 500 milliseconds or fail. So again, I'm going to have to restart because I didn't get JRubble. But fortunately, this is not a large server. This is a little embedded Jetty, so it's going to take about 3 seconds. So that's restarted. So if I do it again, now bear in mind that Wiremock is persistent. It still is going to be delaying responses, but our service should now time out quite quickly. It's the first time I've hit it since I've restarted the JVM, so it still took a while. But here we've flipped to a 500, but we've responded in under a second. Hit that again, it should be around just over 500 milliseconds. So even though our dependency has been slow, it's still taking 10 seconds, we can set it, we can actually respond quickly. If we looked at our response times in our, say, Graphite metrics viewer, we'd see us as responding with 500 and in 500 milliseconds. We'd see the dependency as being slow, and we should probably wake those people up. Not my team, which is good. So are we done? Should we just stop? No. So the next thing we're going to show is why you definitely need to set a connection timeout. So in Wiremock, you can do this thing called reset, which basically puts it back to the original state. So if you're running this as an automated test harness, you can reset it between them. So I'm going to reset, which should mean that my service should become fast again. And it has. So it's done it in 35 milliseconds, followed by 18 milliseconds, which is great. This time, we're going to be in the scenario where our dependency is fine, we're fine, but there's an issue in between us. So we're going to use a command called tc, which is a Linux traffic shaping command. I've got myself a little script here, which is going to run this funky little thing. And essentially, it takes one parameter, and it's going to delay the outbound traffic by that many milliseconds. So I can do a delay of 400 milliseconds. And then I can hit our service again. So do we expect this to succeed? Who thinks yes? It's good, right? Because it's under 500 milliseconds. I hope this succeeds. It's meant to succeed. I shouldn't tell you that, should I? No, it did. It was 200, but it was 419 milliseconds. So we're slow. We haven't hit the 500 milliseconds yet, so we're doing pretty well. We're on the edge. Let's make things worse, right? So let's reset things. And let's say that the network is having a really bad day, and we're going to delay it to 2,000 milliseconds. Who thinks this is going to work? Maybe? Who knows? Oh, it worked. Darn it. No, because we already had a connection established, right? The HTTP client we're using is fine. But what happens if it then doesn't? It doesn't have a connection established. Then we hang, we wait, and we're down to 2.5 seconds, which is not good. We're not doing our job as meeting our SLA. So we can fix this one quite straightforwardly by setting a connection timeout, restart our application. And the great thing I actually like about this as well is we're seeing the exceptions which our HTTP clients, etc. throw, which is really nice because we have Java, it's statically typed language, and then we throw runtime exceptions everywhere. So we just completely circumvent the compiler. And thus, when we go up, say, a 1-point release on all of our dependencies, they can completely change their behavior. But if we have tests like these, we'll know they've changed their behavior. So what we can actually do, because this just says, this is quite small, it says, darn blast, I have no idea what to do. But in reality, we do know what to do now. We can catch the exception which that library throws. Anyway, let's restart this and see if that's fixed our problem. So just to recap, service is fine. We're just delaying each packet now by 2,000 milliseconds, so 2 seconds. Oh, yeah, first one's a bit slow, as we expect. But then, yep, we're failing 500, and then just over 500 milliseconds. It's pretty nice. So are we done? No. So we're going to reset it again, and then we're going to set the delay back to 400 milliseconds. However, our dependency is going to do something which we didn't quite expect. It's going to return us someone with a rather large name. Let's see who his name is. His name is actually a snippet from Wikipedia describing TCP, because you never should trust your dependencies. So we'll just put that prime in. And then we're going to send it back. Not that one. Oh, this isn't good. It was 200, yet it took 2 seconds. What is going on here? No, I don't know. Oh, 1.6 seconds. Now, I would imagine this multiplied down your dependency hierarchy of deciding to spread your service into, 20 different processes running on different boxes with good old cloud networks in between. That's what we did. Anyway, let's go back to the presentation. I'm not going to show you how to fix that one. We will, don't worry. So that demo worked. So I'm counting. So that went pretty well. But what I really want to do is just encourage you to realize that we cannot rely on network level timeouts to implement things like SLAs. And if you're making one external call to one database or say to one HTTP dependency, might happen every so often. But when we turn one of our customer requests into 50 separate calls over the network, this happens, pretty much every request. And if we have a look at a little bit more detail about what could be happening here. So we've got the bit that we expected. We already had this. We take time to get the resource, perhaps, from our HTTP client. We have time to establish a connection. Maybe that connection has been dropped. And then we wait, for a response to come back on that socket. But it has no idea what that message is going to be, right? All it is saying is I'm going to wait so long to read data from a socket. It doesn't need to actually be all of your data. Right? So if your dependency is slow or the network's slow and things are trickling back, and we actually receive a small amount of that data, every 400, every 300 milliseconds, we never actually reach the socket read timeout, which is why we shouldn't implement SLAs with it. Another important note is if you're using frameworks like Spring Boot and Dropwizard, etc., they give you some really cool metrics out of the box. They allow you to record the service time of all of your applications. As soon as the request comes in, say, into your URL, what it then does is it starts a timer, it comes all the way around, and then it stops the timer, and then maybe you can push that metric out to something like Graphite or log it to a file and, pick it up with Splunk or something. If we did that for all of our applications, so we're going to record it. This doesn't work. We're going to record it from the edge of the app under test, and we're going to record it from our dependencies. But what we really want is this, which is the response time from the dependency. And the delay here with that TC command was coming out of the network on the dependencies box. So if we were recording, say, the service time of our dependency and the service time of our application, the application that would be highlighted to being slow would be our application. Right? Because it would slow down our response time to our client. And we could be making 20 different calls out. that metric would not actually be recording, which wouldn't be narrowing down exactly where the slowness is. So we need to make sure we record a response time. And there are actually quite a few instrumented, say, HTTP clients and database drivers, etc., which will do this for us. So we record the service time of every application, but we also record separately the response time when we make calls out. Because, of course, the service time of our dependency is just this. And as far as he's concerned, he is completely fine, right? But what we really want to do is narrow down this, even if we're making multiple calls out. So how do we get around it? Well, I'm assuming most people here, and this project was primarily built on technologies like Jersey and Dropwizard. There was some Spring in there, etc. But they were all synchronous I/O, right? They're all based on servlets. So a thread comes in, it calls do get, but if you're using something like Spring on top or Jersey, etc., it calls your nice controller with your nice annotations. But your responsibility as a developer there is to do some cool stuff, which hopefully means that your company earns some money, and then respond on the same thread. That's your job. What you can't do is give your thread to an external dependency, because they can keep it for as long as they like. And we've got some examples of when this happens when it's not the network. So we can't let that request thread be hijacked. A lot of the new services on a platform which I'm building at the moment are built with a technology called Ratpack, which is a different game where we're going to be using lots of things like non-blocking and asynchronous. And I'll show you a couple of examples of that too. So how do we do it? Well, assuming that we're still in this servlet-based programming model, we have a thread, we have to respond on the same thread, then it's our job to protect it. We're not going to give it to anyone. We're not going to let anyone take control of that thread. And simplistically, you could just put new thread.run throughout your code. .start. Oops, don't do .run. All right? That's not a good idea. You're going to be creating threads. It takes quite some time, etc. So you'll probably use a thread pool, etc. The abstraction for that in Java, of course, having a queue and a thread pool as an executor. Or we could use something like Hystrix. All right? Hystrix basically does this for you. It calls out to dependencies on separate threads, or it uses a semaphore to limit the number of concurrent requests you have out. So you don't use up all of your container threads if you're in a synchronous programming model, calling out to a failed dependency. And it does more than that. It gives you a facility to have a fallback. So rather than just failing because your dependency is slow, you can actually just make up an answer. And we'll show an example of that too. This is a disclaimer. I'm going to show you an example with Spring Cloud, which I think is actually pretty cool. Disclaimer here is I don't use this in production, whereas everything else I do. And rather than having to code this up yourself, Spring can do it for you with a magic annotation. Right? So imagine we have this code here. It's a Spring REST controller. We have a mapping called /scary. Now, if we assume when we call into any of our dependencies, the code really looks like this, we will build vastly more fault-tolerant services. So what all of our dependencies really do is check if the time is even. If it's even, good. If it's not even, they're going to sleep and take that thread from you for 5 seconds, maybe 10 seconds, etc. So let's just assume everyone does this. I put a couple of log statements in just to see what thread we're actually running on. And not surprisingly, Spring Boot uses embedded Tomcat by default. We're using this HTTP 8080 exec1 for both here, both in our controller and when we call into our very scary dependency. So what we've done there is potentially every other request, we're going to sleep for 5 seconds and respond slowly, and we're not going to meet our SLAs. This is pretty cool. So with some class path magic, and a bit of configuration, you can start to just annotate things and guess what happens. So this is basically telling Spring to tell Hystrix that this potentially is an external call or something scary. The only change here is we've annotated the method. And with that very small change, we can see that when we log out, we're actually on a different thread. And then you can configure Hystrix to timeout separately. But if you're dealing with an asynchronous system which offers you an API which perhaps returns a future, you don't necessarily need to do this. Right, so if you look at the Cassandra client, for instance, it is essentially an asynchronous system. It does not use a thread per request out to Cassandra, neither does Cassandra internally. So everything you do with Cassandra is asynchronous. There is an execute method for like executing queries, etc., but all it does is call the async one and then call .get and block. So really, Everything's asynchronous. And of course, once you've got a future, you can time out independently of the network request going out to your HTTP dependency or your database. So sometimes when I'm dealing with these systems, I wouldn't bother wrapping it in a system like Hystrix. And I generally drive this via requirements. So there's a mixture of services which use both. So the first thing I say is I want to write a test to make sure I reliably time out. All right. If I'm dealing with a synchronous dependency, say a relational database or something based on a JDBC, I'm probably just going to wrap it in Hystrix right away. If I'm building with an async system, then I'll probably just use, timing out on the future independently. Maybe then you want to add some throttling. That's an extra feature. At this point, I might consider to start using a framework which is going to offer me this. But as soon as I start wanting to monitor all of the failures and all of the successes and perhaps measuring the response time, say, over the last 10 seconds, at that point, some clever guys at Netflix have done a lot of effort for you. You can just use Hystrix. So that was number one. We've got 4 more to go, but don't worry, they are shorter. All right, and the takeaways from this is essentially do not use network-level timeouts for SLAs. And if someone says you can't test them, just hit them with a stick, because you can deterministically test all of this stuff. And once you've done it for one service, one interaction with one service out to another, it is so, that one did take about a week. But then it takes such a little time to then just have it as your default process. I'm integrating with something over a network. I have this barrage of tests for it, and then you're good to go. And this doesn't always happen when there's actually a problem with the network. If your dependency is overloaded, it's actually going to start dropping new incoming connections. It could be garbage collecting. It could be doing anything. Right? We don't really know whether a dependency is slow or down, etc. So the next thing I noticed that we do a lot, or I certainly did a lot, was trying to do things even though there was no hope in me succeeding. And it reminded me of this. This is a UK post office. Right. UK post offices, if you ever visit the United Kingdom, they are the slowest queues in the world. I'm not sure what's behind this glass window here, but they ain't doing much. Right? And if I would have 5 minutes left of my lunch break, I would not wait in this queue. Yet for many years, I built software that did exactly the same thing. Right? I would queue up and I'd sit in the queue, even though there's no chance I had any chance of getting to the front within my timeout. And this is definitely true. I'm not sure where this quote comes from, but it's definitely not original. So I put it in quotes. But it's not, right? We've got a modern version of this for the JVM and for Java applications. We don't generally send emails, or if we did, we would definitely use a queue and a thread pool to do it. You might not find or see the thread pools and queues right away, but as soon as you actually look inside any framework you're using, any HTTP clients, any drivers, there's going to be hundreds of them. We love them. And we have a really cool facility for doing that inside the JVM, right? We have many, many different implementers of executor services, scheduled executor services, and they're an abstraction essentially around a thread pool and then a worker queue. We even have a really convenient factory for creating lots of them. It's called executors. So you generally don't even look at the constructors and the configuration parameters. How many of these do you think from that executors factory, have a bounded queue? Any of these your favorite? Every single one I've looked into, and every single one that's been in any code I've ever written, has an unbounded queue. And if that queue is in front of a call out to a dependency that is being slow, it gets bigger and bigger and bigger until eventually your JVM, even though there's nothing wrong with you, it's your external dependency, will run out of memory. This is not good because we had the ability to service requests, just not at the rate we were receiving them. So if we're a good service in this respect, we'd start rejecting it. We'd get to capacity, then we'd reject future work. We shouldn't just be optimistic and start queuing at the post office until we actually end up back at work. Okay? We need to start rejecting work. Most of the time, though, it's actually a mission of going into your dependencies and finding all of the places these exist. And if they're not exposed, say the configuration options for changing these queue sizes, etc., then let's hope that the drive you're using, etc., is open source and you can raise a pull request. And again, this type of thing becomes quite easy to produce a test for. I once worked at a company where they wouldn't test this in functional tests, in acceptance tests. They said, "We'll catch that in load testing, etc." Which is often many days later by the time you run a weak soak test. But what you can actually do, let's say we're testing a HTTP client's behavior when all of the connections are in use. right? We can set the timeout to be very high, because in this respect, we don't want a timeout for this test. We can then use Wiremock to add a very large delay. So the requests that are going out are going to hang for a long time. Hopefully, these libraries are going to offer you the configuration to say how many concurrent connections and how many, say, the size of, say, their internal worker queue. Then we can send in 2 requests. One will be called out using the thread, say, and one could be inside the queue. What happens when we send the 3rd request, right? So this is an acceptance test that can run in a couple of milliseconds, right? We send the request, we send another request, then we actually test the behavior on the 3rd. What it is up to you. You can say that request should fail instantly, or if you're testing in a more integrated environment, it should be rerouted via the load balancer to another instance, etc. But we should be writing automated tests for this. So number 3 is fail gracefully. Who here develops a HTTP service or interacts with a HTTP service that produces JSON? Anyone? Most people. XML? Plain text? No. Right. Out of the people who are either integrating with a system that is producing you JSON or XML, how many people have seen a stack trace inside HTML? Most. It's good. All right. We don't do this because we're good developers. However, the services that we're interacting with will always do this to you. So if the first thing you do is try and parse it with, say, Jackson, then bad things will happen, you'll have a nice runtime exception, and things will cascade. And Wiremock, again, is a really cool tool for seeing what your HTTP client does when your dependency is a little bit naughty. So you can write tests for invalid HTTP, which sounds ludicrous until you have a faulty, say, network switch or something, and it literally does send you some invalid HTTP. Malformed response bodies. This can be as simple as expecting it not to be the actual format that the content type says. This happens reasonably often. And until you've actually closed and read the entire thing off the wire, expect runtime exceptions to be thrown. Ideally, have a look at the code on the covers. And the most important one, which we've seen with Mr. TCP Specker's name, is expect a different size response to what you're expecting. And if we look at some of the functionality of Wiremock, we can do some really funky stuff. Here's one. So it has a Java API as well if you don't want to send in JSON to prime it. So you can say, when we call the dependency path, actually send a malformed response trunk. Or we can say, when someone calls /fault, send them an empty response body, even though the content size is rather large. My favorite, though, is this one. If you want to understand what the runtime behavior under failures of your favorite HTTP client is, prime this. Random data, then close. And this sounds ludicrous, but the chances are your HTTP client is going to throw some type of runtime exception that you should catch, you should deal with, and then you should log something useful, say this dependency has sent me some junk, and then fail quickly to your client. As soon as you bump up a version, let's say you test this manually, they could change that entire behavior. They could be using a different runtime exception, they could change to returning null. You just don't know because the compiler isn't going to help you. We actually changed every single HTTP client in the system. We were using a HTTP client, I forget the name, which had a connection pool bug. So we switched over to Apache. We had the tests, which were using real HTTP over real TCP, which meant we could instantly rerun those tests after we committed the change, and we knew exactly if our behavior changed. We were using a completely different HTTP client for that integration, but all of our fault-tolerant behavior should be the same, otherwise our automated test would tell us that it wasn't. I spent my time building the equivalent for Cassandra. So you're integrating with a distributed database. What happens when half of the distributed database is turned off because a hurricane hit New York? Then you could set up a multi-data center spanning across 2 clusters. Or you can use a protocol level test double in which you can just prime it to make your application think that this has happened. And it does that essentially by implementing the same network protocol that the database itself does. So as far as the client is concerned, it's the real database. So the last one, controversially named, is don't hurt horses, or don't hit things which are down. For me, this is quite a popular one now. You know, it's going to come on, but people normally call it circuit breaking. But it's a big, big culture shift. I find this is not a technical problem. This is convincing your business that you should plan for your very fault-tolerant system that they've just paid you a vast quantity of money to build to go down. And everyone's a bit like, what? Why have we hired you? So imagine we were creating the movie player, and to play a movie, we were calling out to a user service to validate a user. And then maybe we were doing some kind of device check to make sure you weren't on 50 devices and giving your password to all of your friends. And then the last check we needed to do was to, say, call a PIN service. Because maybe when you purchase a new movie, they want to check maybe your age. You have to type in a PIN. Or maybe just to make sure that the bill payer can set a PIN so not anyone who comes into the house can't buy movies. What do we do when that's down? Well, we're going to fail quickly. We've already established that. But are we going to fail instantly? Are we going to keep hitting it? If the poor PIN service team are frantically trying to put their service back up and deploy new versions, and the first thing you do is flood them with hundreds and thousands of requests and knock it down again, is that a good idea? Maybe not. So this will happen. However much you put effort into making your services fault tolerant, you'll have a load balancer problem, you'll have a bad release, something is going to go wrong, right? So even though we're putting all of that effort into failing quickly, etc., and dealing with our dependencies being down, at some point, one of them will go down, and we'll need to deal with it, and ideally we'll stop hitting them. One of the most interesting things to do here is to apply fallbacks. So we, as a developer, could just decide, well, I would rather watch Batman and not enter my PIN when the PIN service is down, and you could make that decision yourself, but you probably shouldn't. This is a business decision that you just need to give to them and say, hey, we can either offer you downtime, so a lack of availability, that will obviously annoy customers, or we might let their children buy 50 movies when they thought they were out for a date. That's a business decision. They can make that decision. But in general, I find it very hard to convince companies to actually spend development effort, because it's a reasonably complex problem. I've stolen a picture of the circuit breaker from the Akka docs. I think it's one of the best ones. But it essentially is around all of your dependencies, you're going to keep track of the success rate over a very short period, say the last 10 seconds. You don't care if it failed 3 minutes ago. If too many fail in a short period of time, then you cut it off, and then you can either go to an extremely fail quick. So this is even better than timing out, right? We're not even going to make the external call. Or you can go to a fallback. So we can just basically hard code it to say true or false. Yeah, PIN check's fine. And this is, again, is up to your business. But if your business don't allow you to do this, the easiest one I think to do, and introduce this perhaps without permission, is turning off broken stuff, also called the kill switch. So we don't need a fancy framework like Hystrix to implement a kill switch. We need an if statement. We can do that possibly without permission. Then what we need is maybe some type of dynamic configuration to switch it, or a rolling restart mechanism without downtime so you can actually set the configuration flag. So the scenario I think generally happens is when something bad happens at a weekend, some of the developers get called. Let's say the PIN service is down and no one can buy movies and the company's losing lots of money. What you can then turn around and say is, would you like us to just turn off PIN checking for a short amount of time and we can start getting some money again? And of course your manager says yes, because I'm a freelancer, my weekend rate is very expensive. So he's like, yes, do it quickly and then leave. And then you're the hero. It happens again the following weekend, and he rings you up instantly and says, please press the magic button. Right? And he's very happy about that. When it happens the third week, though, at that point, your manager is going to say, come on, you're a software engineer, don't you automate stuff? Can you please just make sure this happens when they go down? And I generally find once you've had some reasonable outages, which is a terrible thing to say, the business will have buy-in for circuit breakers. And on the system I was discussing at the start, every single call out to every single database and every single HTTP service has a circuit breaker wrapped around, either implemented with code or with Hystrix. So the kill switch can be a really easy one to sneak into an organization to get them thinking that way. So, just to finish up, by far the most important one, biggest takeaway, just remember that you're putting an added complexity if you're going to go down this microservice bandwagon, right? We're going to be calling out over the network lots. We're going to have to deal with lots of slow requests. And just think about 99th percentile. What does that actually mean? It means, say my response time of 200 milliseconds at the 99th percentile, only 1 in 100 customers gets it. But if you make 100 calls, right? And your 99th percentile suddenly becomes a lot more significant. Let's just forget that we do not want to go to, if we go to the UK, do not want to send any mail at a post office. This is extremely important. And of course, we're going to expect everyone else to fail badly. But when they do, we're going to stop hitting them, right? We're going to use techniques like circuit breakers, and we can sneak those in with things like kill switches. If you want to take a look at the examples or play around with the demo, that is the Vagrant Wiremock Saboteur. The priming I did inside the Google Advanced REST client, you can actually export those as projects, so you can have all of the primes. That's also checked in the project, so you can also do the priming, etc. I definitely suggest people have a read up on Hystrix. Even if you don't use it, read the documentation, and it will make you think of all of the things which a very large organization has found have gone wrong and have automated ways to deal with. So it's quite educational. And if you want to actually have automated tests for these network faults, etc., definitely have a look at Saboteur, because what it is essentially a nice little REST interface around the commands we were running on the command line. So on that note, I will say thank you for listening, and hopefully everyone enjoys the movie tonight, and thanks very much.